Alright, let's learn how to use our M2K or the ADLM2000 function generator and oscilloscope functions. Alright, when you start Scopy, you can see this nice picture. We only have half the wires. This is to use the digital ports. We're just using the analog ports. And here's everything that comes out, and what we're going to do is connect these back into themselves with male-to-male wire as shown in the lab manual. So we just connect, and it calibrates, and we should be ready to go. And here are all the various functions. We have power supplies, oscilloscopes. You can move these around, so if your order isn't in the exact same order that mine is, that's okay. We're going to do oscilloscope signal, and we're even going to get a little bit to the spectrum analyzer today. So first thing we need to do is create some signals. So let's look at channel 1, and if I click down here, that comes to settings, and you can have a constant, right? You can see that orange line move up and down. We can have a waveform, and that we can have a sine, square, triangles, sawtooths. You can even add noise, okay, to various degrees. We have a buffer, which this is a noise file that I'm reading in. So you can process something in LT-Spice and read it into Scopy. And then we even have some math functions. And I'm going to get into that later. But right now I just want to do a sine wave. And now I want to see channel 2, which I had some math examples. And I just want to do another sine wave of different frequency. Alright, here controls the amplitude, right? Smaller, larger. V peak to peak is twice whatever, or no, this is in V peak to peak. It's not the number you scale a sine wave to from, so it measures from here to here. So 2 volts peak to peak. I go down 1 volt, down another volt, that's 2 volts. 5 hertz. We can increase the frequency. Now it's the same frequency as the other waveform, so you couldn't see it. You can delay it, you can offset it, you can add noise. Now nothing will happen until you click run, alright, which now it's sending out these waves on W1 and W2. W1 is orange, W2 is the purple. So let's go to the oscilloscope. Doesn't look like anything's going on because we have to run it. Alright, and you can see something there, but we might have to zoom in. Okay. So here, right, this is volts per division, so that's 2 volts for every square. So if I want to zoom in, I have to lower that, right? And then the time base is 20 milliseconds per division. So if I want to zoom in, I make it smaller, right? And interestingly, something is going on with channel 1, which generally means something fell out. So I'm just rechecking my wires. I'll double check. No, this is here. That's what I should be getting. So I'm making sure, and yep, you can't see it, but I accidentally wired the power supply into that channel. That should have fixed it, and there we go. So unfortunately it's hard for me to show you what I did, but there was no signal and it was wired into the wrong thing, and I fixed it. And I'm actually going to leave this in the video because that happens, right? It's just I don't have a studio where you can see me do the screen and see me fix a problem. All right. Now, so if you want the most accurate time measurements, you try to zoom into where you're getting about 2 periods or 3. You can leave it at that. Right. Now this is at a higher frequency, and so I can't zoom in this one, otherwise the lower frequency waveform you won't see the whole thing. All right, and I can try to zoom in, and you don't have to use whatever it tells you. You can put in 250, right? And then if I click down here on channel 2, I can do the same. Just make sure I'm getting the most accurate measurement. And then here it's giving me some measurements, the peak to peak voltage, the mean, all right, and the frequency. And there's other measurements that we can do. You can click here and you can display everything, right? So it's got the min value, cycles, RMS, which is important. There's a little toolbar here. That's where you can see everything for channel 1. And there's just really so much, I can't go into it all. But I'm going to turn this off. It's a little distracting though to see everything. Okay, so I can turn off the measurements, all of them like that, and then here I can select what I want. And there's other things that you can measure, like frequency, rise time, fall time, duty cycle, right? And then clicking down here just turns it completely off. Now there's some other interesting features. We have the XY plot, where if I turn that on, the x-axis is now channel 1, right, which is at this frequency, the orange, and the y-axis is channel 2. You get that symbol, right? We can, let's go back to the signal generator. So I'm at 200 hertz here for the blue. Let's do 210. Go back to the oscilloscope, and now you can see this pattern doesn't stabilize. All right, which is pretty cool. Then there's something also called the FFT, which it's better to show us somewhere else. So I'm going to just turn that off and turn this back to 200 hertz. So there's other settings, right? How thick the channel you want. Do you want lines? You can have dots. You can have steps, sticks. Right? You probably have to zoom in to see what that really. It's taking so many measurements that you can't really see the steps or the sticks. or even the dots. AC coupling will remove any DC offset, right? And snapshot, oops. I accidentally put this snapshot here. I don't want it, so I'm getting rid of it by clicking on that. You can print this. Put it in downloads. Okay. It doesn't necessarily give you all the detail you need. That's why I tend to use Snagit or something like that. Okay. And then here, export, I can put it into a CSV file and then actually read it into Python for what I would say really nice plotting. All right. So let's look at the spectrum analyzer. So this, you can tell, I can measure this and see what the frequency is and kind of by eye find the amplitude. But the spectrum analyzer does this automatically. So we had a 100 Hertz wave and we had a 200 Hertz wave, and this magnitude is indicating that's what we have. Now it doesn't tell you the phase, but it is telling you that there is a sine wave at this frequency and a sine wave at that frequency. Now let's go look at different signals now. So obviously a constant would be a constant. Waveforms are going to be waveforms. But here's a square wave, right? We can see it's still at the same frequency, but square waves are made up of an infinite number of sine waves. It's called the Fourier series, and we can see that in the spectrum analyzer. So we have a sine wave at this frequency, and then a sine wave at 3 times that, 5 times, 9 odd harmonics. All right. Triangle wave has a different series, but it's still made up of an infinite series. All right, of different. All right. Now again, here is, you can load in a file, but I had some math functions already set up. And I really have cosine t. Now this is really cosine, there's a scale factor in here it's 100 Hertz times 2 pi. So if I put in cosine t and set that to 100 Hertz, it's 100 Hertz cosine wave. You don't have to, it's not pure time, the units are different. But what we have here is a 100 Hertz cosine, then a 300 Hertz minus a 500 Hertz, and you see this function here. When we go back to the spectrum analyzer, you can see, oh, there's our 100 Hertz, there's our 300, and there's our 500. It broke it out for us so that we could see it. Everything has the same magnitude because I scaled it that way. Right, everything was scaled by 1. Now this is in RMS. We can also, there's other units. More than likely this is what you'll come up with. All right, And so to kind of get the same picture, you have to click on sweep. Here I have it as a logarithmic sweep, right? And that's where it starts, and this is where it ends. And what happens is it's not accurate at low frequencies when you're going all the way up to 25 or 50 megahertz. So it starts at 1, I keep bringing it down, and then we start to see our units. And this is dBFS. There's just dB in volts, okay, and then there's peak, right? So it's not in dB, so you have to scale it. So you can tell it goes up to 1, and then the range is 1. Now we're getting now you can see that amplitude is 1, 1, and 1, and you can see it pretty well. All right. And again, how to do that is you're clicking on sweep, and it controls it for both channels. Right? You can do it linear, but see how now everything is squished here, and I have to kind of zoom in. Now I'm on a linear scale. All right. But this is really important, just stochastic resonance, because you're trying to see a signal and it's got noise on it, and can we detect it? Right? If we go back to our sine wave here and add noise, right? You can tell there's a sinusoid in there, but I'm going back to logarithmic scale. And now I'm just going to turn off channel 2 by clicking that dot. So see, I'm still at I can still see that peak, but all of this over here is the noise that I added, right? If I come back to the signal generator and just turn the noise off and come back to the spectrum analyzer, you can see that it's down to close to 0. And this peak to the background is the signal to noise ratio. All right. Let's see, how much noise can I put in there? Oh, 10 is about it. Then one thing is what I'm going to do on channel 2 is we'll go back to a waveform, and I'm going to have a square wave, and let's have that at 100 Hertz. And then channel 2, I want to go to the math. All right. And what I have here are a progression of sine waves, one at 100, one at 300, one at 500, and I'm scaling it. I'm actually scaling it by these Fourier coefficients. And notice how it's actually started, when I start summing these up, it's actually starting to look like a sine wave. Now I'm going to have everything at the same. So the more I add, the closer it approaches. Now I'm not going to go into it here, but you can never add, you can keep adding, but there'll always be some overshoot. It won't be perfect. All right. So now let's go back to the spectrum analyzer, turn on both channels. All right. The orange, right, is made up of a 100 Hertz, 300, and 500 scaled, right? And then the actual square wave has the same 100, 300, 500, and then the rest of the harmonics. But these are all sine waves that we decomposed. And the spectrum analyzer, it's really like a prism, and it can split up light that you can't tell exactly what frequency it's at into your red, blue, green, whatever you feel like. Alright, so you might have to watch this a few times to get what's going on. The important things are that these here will control your individual window characteristics, right? You can turn things off and on by clicking on them. If you want to see the sweep, right, that's where you start and that's where you end, and this is your scale. And dBs, you know, compresses this so you can see things more easily. Alright, but you can see the first three harmonics here. Stopping and starting, if I wanted to go back and see what it is on the oscilloscope, it stopped, so I have to click run, and now I'm seeing that. Right, I can do the XY. That's interesting. Right, it does have an FFT, but you have to go and change the time base before you can see what's going on. Alright. And it does have some issues here that I'm not going to get into. So when you want to see the FFT, it's better to go to the spectrum analyzer. Again, signal generator, you can have constants, sine squares, right? We didn't go over reading a file in, and then you can have mathematical options. And notice it never stopped, right? I just switched to buffer, or I switched to waveform, and I go back and it's already changed when I get there. All right. You can save all these configurations, but it's usually set up to have everything saved when you exit to whatever the last thing it is that you were doing. All right. Have fun.